Have you ever actually stopped to think about the sheer mind-boggling journey required to power our modern world? I mean, we're talking about an epic, millions of years saga of immense pressure, hiding right beneath our feet, just waiting to be unlocked. It is a world of extreme engineering, prehistoric mysteries, and seriously high-stakes exploration. Okay, let's dive into this.
Here is the roadmap for our highly structured virtual expedition today. We're going to start at the surface with the 3 petroleum streams, then journey deep underground to see how hydrocarbons are born and explore porosity and permeability. After that, we'll look at searching the subsurface, compare conventional versus unconventional reservoirs, and finally, bring the prize back up to grade the crude oil.
All right, part 1, the 3 petroleum streams.
So before we really begin our descent into the Earth, we need a macro view of the entire oil and gas industry. It's basically divided into 3 massive sectors. Downstream is all about refining raw petroleum into products like gasoline and plastics, right down to the retail sales at your local pump. Midstream, that's your transportation and storage. Think massive cross-country pipelines and giant ocean-crossing tankers. But upstream, that is where the magic happens. Upstream is completely focused on exploration and extraction. It's about actually finding and pulling the oil and gas out of the ground. And for this explainer, we are focusing exclusively on this high-stakes, highly complex upstream world.
Moving on to part 2, how hydrocarbons are born.
Okay, we are literally traveling millions of years back in time, deep underground, to witness the slow, fascinating birth of this energy. It all begins with microscopic, prehistoric marine organisms settling on the ocean floor. Over vast stretches of time, they get covered by incredibly heavy sediment layers. Deep underground, these materials get pushed into a highly specific geological sweet spot we call the oil window. Subjected to intense heat and immense pressure, this organic matter undergoes a complete chemical transformation, eventually becoming the crude oil and natural gas we extract today.
Now, what's really interesting about this slide is how 3 highly specific rock types have to interact perfectly to form a natural underground trap. First, you have the source rock. This is organic-rich rock like shale where the hydrocarbons literally form. But the oil doesn't just stay put. Over time, it migrates into the reservoir rock. This is a porous rock, like sandstone or limestone, acting kind of like a giant subterranean storage unit. Finally, you absolutely need a lid to keep the prize from just seeping right up to the surface, and that's the cap rock. This is an impermeable layer, something like salt or dense clay, that sits right above the reservoir, securely trapping the oil underneath.
Part 3, porosity and permeability.
So now that we have these trapped hydrocarbons, let's talk about the actual physical mechanics of how liquid behaves while trapped inside solid rock. Reservoir rocks are uniquely characterized by their porosity. Basically, that's the percentage of empty space or voids within the rock structure. Just picture a standard kitchen sponge. From a distance, it looks totally solid, right? But zoom in, and it's full of tiny holes that hold water. Well, reservoir rocks are exactly like that. They're nature's stone sponges, capable of storing immense amounts of fluid, like oil, water, or gas, right inside those microscopic pores. But here's the catch. Storing fluid is really only half the battle. The fluid actually has to be able to move. And that brings us to permeability. This is the ability of fluid to physically flow through interconnected pores in the rock. To bridge the gap from just storing to flowing, imagine pouring water through a coffee filter. The water passes through easily because all those microscopic pathways are connected. High permeability means the pores in the rock communicate with each other, letting the oil travel easily toward a wellbore when we finally drill down to find it.
Part 4, searching the subsurface.
Now we shift our perspective to the explorers. Think of them as modern detectives trying to map these dark depths from all the way up on the surface. How do we find microscopic pores filled with oil hiding miles underground? Well, we use geophysical exploration, specifically by bouncing sound waves off underground rock layers. For decades, the industry relied on 2D seismic surveys. These use sound waves to provide vertical, cross-sectional slices of the Earth. It's kind of like looking at a single slice of bread from a whole loaf. But modern exploration has made an incredible technological leap to 3D seismic surveys. This creates highly complex, 3-dimensional volumetric maps of the subsurface structures. So instead of one flat slice, explorers now have a complete, rotatable digital model of the entire underground landscape.
But, even with all this amazing 3D data, eventually, you just have to prove the oil is actually down there. Enter Wildcat drilling. This is exploratory drilling in a completely unproven, uncharted area to test for new deposits. This is the absolute frontier. It's high stakes, it's high risk, and it is incredibly expensive. You are putting a drill bit deep into the earth based on scientific, educated guesses, hoping to strike entirely new, untapped reserves. It's literally the modern equivalent of exploring uncharted territory.
Part 5. Conventional versus unconventional reservoirs.
So, let's talk about the engineering hurdles we face when we finally locate the oil, but the geology stubbornly refuses to let it out. We generally run into two main types of reservoirs. First, we have conventional reservoirs. Remember permeability? Well, conventional reservoirs have high permeability. The pores are beautifully connected, meaning the oil and gas flow naturally and easily right into the wellbore. But then, you have unconventional reservoirs, like tight shale formations. These have incredibly low permeability. The oil is trapped inside, but it cannot flow on its own. To extract it, engineers have to use artificial cutting-edge techniques, like hydraulic fracturing, commonly known as fracking, and horizontal drilling, to essentially create artificial permeability and force those stubborn hydrocarbons out.
And finally, Part 6, grading the crude oil.
We are making our final ascent back to the surface. The extracted treasure is up, but before it hits the downstream market, it has to be evaluated. So the crucial point is this 31.1 degrees API threshold. API gravity is a specialized metric measuring how heavy or light crude oil is compared to water. Anything grading above this 31.1 mark is classified as light crude. It floats easily, flows beautifully, and is highly valued because it is so much easier to refine into high-demand products like gasoline. On the flip side, crude below 22.3 degrees API is considered heavy. It's thick, sluggish, and just much harder to process.
But beyond weight, the chemical composition is just as vital. Specifically, we're looking at a strict threshold of just 0.5% for sulfur content. If that crude oil contains less than 0.5% sulfur, it is graded as sweet crude. And sweet crude is highly sought after because it's significantly easier and cheaper to refine. But if it contains more than 0.5% sulfur, it becomes sour crude. And sour crude requires some heavy-duty processing-heavy techniques to strip that sulfur out before it can really be used.
We've covered a massive amount of ground today, literally and figuratively. So I have to ask, when you use a simple plastic product or fuel your car today, will you remember the millions of years of immense pressure and cutting-edge science that brought it to the surface? The energy that powers our world doesn't just magically appear. It is the breathtaking result of prehistoric marine life, massive geological forces, the precise interaction of rock layers, and the relentless engineering required to find it and bring it up. Next time you hold a piece of modern convenience, I hope you take a second to just be in complete awe of the epic, unseen upstream journey behind it. Thanks for joining me on this explainer, and keep exploring.